close your eyes now, if you'd like. There is no hurry. There is nowhere you need to be, nothing you need to do, and no one waiting for you to do anything at all. The day is finished. Whatever it carried, whatever weight it pressed into your shoulders, whatever noise it poured into your ears, all of that is done. It is behind you now, like a shore you have gently sailed away from, growing smaller and quieter with every slow breath. You are safe. You are warm. You are here. And here is a very good place to be. Tonight we are going to travel together, not in any hurry, not with any urgency, but slowly and peacefully, the way a feather drifts down from a great height, turning gently in the air, in no particular rush to arrive anywhere at all. We are going to travel through space, not the loud, dramatic space of movies, with flashing lights and engines roaring and things exploding in colorful bursts. No. We are going to travel through the real space, the quiet space, the kind of space that stretches beyond anything your mind can fully picture, vast and dark and almost impossibly still, filled with objects of extraordinary size and beauty that have been burning and drifting and slowly changing for billions of years, long before this planet existed, long before anything alive had yet opened its eyes. Tonight we are going to visit some of the most extraordinary stars in the universe. Some people call them the scariest stars, and perhaps that is not entirely wrong. They are immense. They are powerful beyond any description that truly captures their scale. They do things that seem impossible, that seem like the stuff of ancient mythology, of stories told by firelight to explain the incomprehensible sky. But I want you to hear about them the way you might hear about a great sleeping mountain. Not frightening, but awe-inspiring. Not threatening, but humbling. The kind of thing that reminds you how enormous and old and endlessly fascinating this universe is, and how small and peaceful and safe your little corner of it is, right here, right now, wrapped in warmth. So breathe with me, just for a moment. Breathe in, slowly, fill your chest with air, and breathe out even more slowly, letting every muscle soften just a little more than before. Good. Let's begin. Part 1. The night sky above you. Imagine for a moment that you are lying on your back in a wide open field. It is late evening. The last light of sunset has melted away on the western horizon, leaving only the faintest bruise of purple behind. And above that, the first stars are beginning to appear. Not all at once, they don't do that. They arrive one by one, shyly, like visitors unsure of their welcome. One small pinprick of white light here, then another there, then slowly, slowly, the whole dark dome above you begins to fill with them, until the sky is a deep, velvety black scattered with thousands of tiny, trembling lights. The grass beneath you is cool and soft. The air smells like earth and night-blooming flowers and something clean that has no name. There is a silence so complete that you can hear your own heartbeat, steady and slow, like a distant drumbeat at the edge of a quiet forest. And you look up at all those lights, and you let yourself wonder, because wondering is one of the most restful things a human being can do. It opens the mind gently, the way a flower opens in morning light, without force, without effort, simply unfolding. You wonder, what are those lights, really? You know the answer, in the same way you know many things, loosely, quietly, without needing to grip it too tightly. Those lights are stars. Each one of them is an enormous ball of gas, mostly hydrogen and helium, held together by its own gravity, burning at temperature so extreme that the numbers barely mean anything to our everyday minds. Each one is so far away that the light reaching your eyes left its source years ago, decades ago, centuries ago, sometimes millions of years ago, traveling at the fastest speed anything in the universe can move, crossing distances that make even the widest ocean seem like a puddle. Most of those stars, the ones you see with your unaided eyes, are something like our own sun, medium-sized, medium bright, steady burners that have lived for billions of years and will continue to live for billions more. They are the ordinary citizens of the cosmos, and even they are extraordinary. Even they are almost impossibly large compared to anything on Earth. But they are, in the grand scale of things, the quiet neighbors, the unremarkable ones. Tonight, we are not visiting the unremarkable ones. Tonight, we are going to seek out the giants, the true giants, the stars so large, so brilliant, so strange, that when astronomers first found them and measured their sizes, the measurements seemed wrong, seemed like mistakes, seemed like something the instruments had gotten confused about, because the numbers were simply too large to believe. But the numbers were right, and when you understand just how large, just how bright, just how utterly magnificent these stars are, something strange happens. You don't feel afraid. You feel calm. You feel the particular kind of calm that comes from understanding your own smallness in a universe of boundless wonder, and finding, in that smallness, a kind of peace. Because you are very small, it's true, but you are also here. You are present. You are alive on a small, rocky world that orbits an ordinary star, tucked safely in one of the quiet outer arms of a galaxy, that itself is only one among hundreds of billions of galaxies. And somehow, against all odds, in all this vastness, you are conscious and warm and breathing, and that is its own kind of miracle. Now, let the field go. Let the cool grass go, and the night breeze, and the faint smell of flowers. We are leaving the surface of the earth behind. Slowly, gently, no sudden movements. The planet grows smaller beneath us as we drift upward, the lights of cities forming soft clusters like glowing moss on a dark stone. And then even those lights fade, and we are in space, in the true dark between worlds. Breathe. All is quiet here. All is still. The stars ahead of us are brilliant and many, and we have a long, peaceful journey to make. Part 2. First stop, our own familiar sun. Before we venture out to the giants, let us say goodbye to the sun we know. It is behind us now, receding, and as it shrinks with distance it becomes simply another star, a point of yellow-white light among many, and then it is gone, swallowed by the dark. But before it went, let's remember what it was. Our sun, the one that warms your skin in summer, that makes shadows on winter afternoons, that lights up the morning and sets the sky on fire at dusk. Our sun is, by every measure that matters to daily life, enormous. It is so large that if you could hollow it out, you could fit about 1 million Earths inside it, with room to spare. Its surface is roughly 10,000 degrees Fahrenheit, hot enough to vaporize any material you can think of, to turn rock and iron and everything else into gas in seconds. And below the surface, at its core, where the real work of being a star happens, the temperature reaches about 27 million degrees Fahrenheit. And under those conditions, hydrogen atoms are crushed together so forcefully that they fuse into helium, releasing energy, the same energy that eventually becomes the sunlight on your face. It has been doing this for about 4.5 billion years. It will continue for about another 5 billion, and it will never know that you exist, or that you are thinking about it right now, drifting away from it through the quiet dark.
It simply burns, and is always burned, an enormous, patient furnace at the center of our small solar family. That is the sun we know. Now, imagine something so much larger that our sun, held up beside it, would be like a grape held up next to a hot air balloon, or perhaps a marble beside a castle. The comparisons get difficult because the scale differences are simply so extreme that our minds, evolved to navigate environments measured in feet and miles, genuinely struggle to accommodate them. But we are going to try. We are going to try, and it is going to be wonderful, because we are heading toward Betelgeuse. Part 3. Betelgeuse, the Red Giant. Say the name quietly to yourself if you like. Betelgeuse. It is an old name from the old sky-watching traditions of Arabic astronomers who watched the stars every night from desert landscapes and gave names to everything they saw, cataloging the heavens with the care of librarians cataloging an infinite collection of books. The name comes from words meaning something like the hand of Orion, or perhaps the armpit of the central one, depending on which translation you follow, because this star was part of the great constellation Orion, the Hunter, one of the most recognizable patterns in the winter sky of the northern hemisphere. And right now, from the comfort of wherever you are drifting toward it. Betelgeuse is about 700 light years from Earth. That means the light leaving it right now will take 700 years to reach Earth. And when we look at it in our telescopes and with our instruments, we are seeing it as it was 700 years ago, in the medieval period on our world, when cathedrals were being built in Europe, and empires were rising and falling across Asia, and explorers were beginning to wonder what lay beyond the edges of the maps they had drawn. 700 years, and light, which moves at almost 300,000 kilometers per second, is only now arriving from that distance. The universe is very, very large. But we are not traveling at the speed of light on this journey. We are traveling at the speed of imagination, which is instantaneous and also somehow slower than anything, because it lets you linger wherever you want. So let us linger for a while on our approach to Betelgeuse. As we get closer, something remarkable begins to happen. The star ahead of us, which from Earth looks like a small reddish-orange point of light, one of the two bright shoulders of the constellation Orion, begins to grow. It grows, and it does not stop. And there comes a moment when you realize that what you thought was going to be a star is now filling your entire field of vision, and it is still growing. And what you are seeing is not a star the way you think of stars, not a neat burning sphere the size of a city or a moon, but something that fills the sky the way a sunset fills the horizon, wall to wall, edge to edge, warm and glowing and ancient. Betelgeuse is a red supergiant. It belongs to a class of stars that represents the late stage of life for very massive stars, a phase they enter after billions of years of burning hydrogen, when the hydrogen in their cores begins to run out and the star swells, dramatically and slowly outward. Not violently, slowly, the way a loaf of bread rises in the oven, but on a timescale of millions of years rather than an hour. Betelgeuse has swollen to a size that is genuinely difficult to state without seeming like you are simply making up large numbers. Its radius is approximately 700 times the radius of our Sun. If you placed Betelgeuse at the center of our solar system, where our Sun currently sits, its surface would extend out past the orbit of Jupiter. In some estimates, past the orbit of Saturn. Let that settle in for a moment. Mars would be inside this star. The asteroid belt would be inside this star. Jupiter, that enormous gas giant, so large that all the other planets in our solar system put together could fit inside it. Jupiter would be somewhere inside the outer layers of Betelgeuse, immersed in its gas and plasma, not even close to the star's center. And yet it is not the largest star we will visit tonight. But let's not rush. We are here now, drifting near the surface of this extraordinary object, and there is so much to notice, so much to simply be present with. The surface of Betelgeuse, if you can call it a surface, and it's not quite right to do so, since it doesn't have a sharp edge the way a planet does, but rather a kind of gradient, a place where the gases thin out and the light escapes into space, is covered in enormous convection cells. Imagine the bubbles on the surface of a pot of boiling water, but each bubble the size of our entire sun or larger. Hot gas rises from the interior, reaches the outer layers, cools slightly, and sinks back down. And in this rising and sinking, the surface of Betelgeuse churns and roils in slow, enormous waves. The color is extraordinary. It is red, yes, a deep, warm, ruddy red, the color of a coal almost burned out but still radiating heat, or the color of the sky in the moments after a great sunset, when the color lingers even after the sun has gone. But there are variations within that red, brighter patches and darker patches, and when instruments are used to map the surface, they reveal a landscape of breathtaking complexity, constantly, slowly, majestically in motion. Betelgeuse is also a variable star, which means its brightness changes over time. It pulses, in a way, not quickly, but over months and years. It brightens and dims in long, rhythmic cycles, as the star itself breathes in and out on timescales that dwarf anything we can easily grasp. In late 2019 and early 2020, Betelgeuse dimmed significantly, noticeably dimmer to observers on Earth, enough that people began to wonder, is this it? Is Betelgeuse about to die? Because, you see, Betelgeuse is not young. It is a massive star that has burned through its fuel at a prodigious rate. Massive stars burn bright and fast, and though Betelgeuse is only about 8 to 8.5 million years old, compare that to our Sun's 4.5 billion years. It is already near the end of its life. Astronomers believe it could go supernova, could explode, at some point in the not-too-distant astronomical future. Perhaps in 100,000 years, perhaps sooner. Perhaps from the universe's perspective, almost any moment. But that dimming in 2019 and 2020 turned out to be caused by something more poetic than a stellar death knell. Betelgeuse had expelled a large burst of gas from its surface, and that gas, cooling as it moved away from the star, condensed into dust, a cloud of tiny particles that temporarily obscured part of the star's light, like a veil drawn briefly across a lantern. The star was shedding itself, exhaling. Stars like Betelgeuse are always doing this in a way, always losing mass, always sending material outward into the space around them, like a great shaggy creature that perpetually sheds its fur. The region of space around Betelgeuse is filled with the material it has lost over its lifetime, a vast, diffuse cloud of gas and dust that extends far beyond the visible star itself, catching the star's own light and glowing faintly, a whisper of a nebula, a pale orange haze surrounding this ancient red giant. It is very beautiful, in an understated way. Drift here for a moment. Feel the warmth of it. Imagined warmth, but warm nonetheless, the way a hearth fire is warm even when you are not standing right next to it. Betelgeuse radiates an enormous amount of energy, far more than our sun, though its light is redder, deeper in wavelength, less of the blue and violet end of the spectrum, and more of the oranges and reds. If you were a planet orbiting Betelgeuse at the right distance to be warm, the star would fill nearly your entire sky. Not a disk as our sun appears from Earth, a manageable disk you can blot out with a thumb at arm's length, but something that would stretch from horizon to horizon, a vast dome of deep red light. Imagine waking up to that sky. Imagine the light it would cast on the landscape, warm and ruddy, like perpetual sunset, making everything look like the last hour of afternoon, all long shadows and golden red glow. It would be beautiful. And it would be, in the end, temporary, as all things are. But for now, Betelgeuse burns. It has burned for millions of years, and even if it were to explode tomorrow, to go supernova and briefly outshine every other star in our galaxy, visible even in daylight from Earth's surface for weeks or months, the explosion itself would pose no danger to Earth. 700 light-years is an enormous distance. We would see it, we would marvel, and then we would watch as the remnant glowed for years, fading slowly, leaving behind either a dense stellar remnant spinning at tremendous speed in the dark, or perhaps a small black hole, a new chapter for the material that had been Betelgeuse. All things change. All things, given enough time, transform. But we have no need to hurry that process tonight. Let the red giant burn. Let it pulse and breathe and slowly exhale its outer layers into space. It has been doing this for millions of years, and it can continue without our attention. We are moving on. Let the warm red light fade behind us as we drift deeper into space, toward something even larger, even more remarkable, even more astonishing in its sheer scale. Part 4. The fabric of the space between stars. Before we arrive at our next destination, let us take a moment to appreciate the space between. Because space is not, as it might seem from the outside, simply nothing. It is something. It is a medium filled with very thin gas, with occasional dust particles, with magnetic fields threading through it like invisible rivers, with the remnant light of ancient events that occurred billions of years ago, still traveling, still spreading out in all directions, already so diluted that no instrument can easily detect it. The space between stars, the interstellar medium, as astronomers call it, is extraordinarily thin. If you scooped up a cubic meter of the material that fills the space between stars in our galaxy, you might find, on average, about one atom in it. One single atom, rattling around in a cubic meter of what might as well be called vacuum. And yet across the distances of the galaxy, this thin material adds up. It gathers into enormous clouds, called nebulae, that are visible from Earth as faint smudges of color in the night sky, or as dark patches where the gas is thick enough to block the starlight behind it. Some of these clouds are among the most beautiful things in the known universe, glowing in colors that no sunset on Earth has ever matched, lit from within by the radiation of young, hot stars buried in their hearts. We pass through one of these clouds now, in our imagined journey, and the effect is extraordinary. The light of distant stars dims slightly as the cloud's thin haze gathers around us, and the darkness takes on a faint quality, a slight luminescence, as if the space itself were glowing very gently, which in a sense it is. The particles in these clouds are mostly hydrogen, the simplest and most abundant element in the universe, the element that stars are born from, and that stars spend their long lives fusing into heavier things. There is also helium, and small amounts of carbon, oxygen, silicon, elements forged in the hearts of earlier generations of stars that lived and died before our sun was born, seeding the surrounding space with the products of their nuclear furnaces, the material from which everything that came after was made. You are made of that material. The calcium in your bones, the iron in your blood, the oxygen in your lungs. These atoms were made in stars. Not our sun. Our sun is too small and too young to have made them. But earlier stars, larger stars, stars that lived fast and bright and ended in spectacular explosions that scattered their contents across the galaxy like seeds scattered across a field. And those seeds gathered again over millions of years, and some of them became our sun, and some of them became the planets around our sun, and some of them became the oceans and the land and the living things upon the land, and some of them became you. You are, in a very literal sense, made of stars, and the stars you are drifting toward tonight are your ancient relatives, your distant kin, members of the same family of cosmic objects that eventually gave rise to everything you are and everything you have ever known. That is a thought worth sitting with for a moment. Sit with it the way you might sit with a warm drink on a cold evening, just holding it, letting the warmth spread through your hands. We drift through the nebula. The colors here, if our eyes could see them properly, and for the purposes of this journey they can, are magnificent. There are deep reds, the color of hydrogen gas excited by ultraviolet light and re-radiating it at a specific wavelength, a color called H-alpha that happens to fall in the red part of the visible spectrum. There are soft blues and greens from other gases, oxygen, sulfur, ionized by the radiation of nearby hot stars and glowing in their own characteristic colors. There are dark lanes where the dust is thick enough to block everything behind it, silhouetted against the glowing gas like ink brushed across a watercolor sky. We float through it all, very slowly, very peacefully. And on the other side, The dark opens up again, deeper and quieter, and ahead of us, still impossibly far but growing slowly larger in our perception, is our next destination. Part 5. UY Scuti, the largest known star. The name is not poetic. UY Scuti. It comes from the star's catalog designation. UY is part of a labeling system for variable stars, and Scuti refers to the constellation Scutum, a small, faint constellation in the southern sky, not far from the center of our galaxy. If you look at Scutum from Earth without a telescope, you see mostly the vast, hazy band of the Milky Way in that direction, the combined light of hundreds of billions of distant stars, blurred together into a luminous cloud. Somewhere in that glow, almost hidden by the dense star fields in the direction of the galactic center, sits UY Scuti. And UY Scuti is, to the best of our current measurements and understanding, the largest known star in the universe. Not the brightest, not the most massive, but the largest, in the sense of physical volume, of sheer radius, how far from the center to the edge. Its radius is approximately 1,700 times the radius of our sun. Let's try to understand what that means. Imagine you are an ant, and you want to walk around the circumference of a soccer ball. That walk would take you some time, a few minutes perhaps at a brisk ant pace. Now imagine that instead of a soccer ball, you need to walk around a sphere the size of a house, then the size of a city, then a country, then a continent. Each time you think you have a handle on the scale, the size increases again, and you adjust, and then it increases again.
Our sun, if you traveled around its equator at the speed of a commercial airplane, about 900 kilometers per hour, would take about 6 months to circle. 6 months of continuous flying. UY Scuti's equator at the same speed would take about 1,000 years to circle. 1,000 years, the same length of time that separates us from the year 1025 AD, when the Viking Age was winding down, and the Aztec civilization had not yet risen, and the Black Death had not yet swept Europe, and Shakespeare had not yet been born, and the Americas were not yet known to European explorers. All of that time, all of those centuries of human history, art, war, love, invention, discovery, loss, and change. That is the time it would take to fly around UY Scuti's equator in a commercial airplane. It is genuinely difficult to know what to do with that information. The mind reaches for it and finds it slipping away, too large to hold, like trying to cup water in open hands. And yet here we are, drifting toward it, and there it is ahead of us, another red hypergiant, like Betelgeuse, but even more extreme, even more swollen and distended, a vast sphere of gas that seems less like a star and more like a small glowing world unto itself. The surface of UY Scuti, again using the word loosely, since these red supergiants and hypergiants have no hard surface, only a gradual thickening of gas, is turbulent in ways that our instruments can barely resolve. Enormous plumes of gas rise and fall on its outer layers, convection cells that would each dwarf our entire solar system. The star itself pulses, varies in brightness over a period of roughly 740 days, a cycle of brightening and dimming that corresponds to enormous internal oscillations, the star itself expanding and contracting slightly over periods of 2 years at a time, breathing in and out on the longest of timescales.
UY Scuti is about 9,500 light-years away from Earth, much farther than Betelgeuse, buried deeper in the galaxy, hidden in the dense star fields of the inner Milky Way. When you look in its direction, you are looking almost toward the center of the galaxy, where the stars crowd more tightly together, and the interstellar medium thickens with gas and dust, and the sky, seen from any hypothetical planet in that region, would be ablaze with the light of thousands of nearby stars. We are far from Earth now, very, very far from the small blue world where you are lying, warm and breathing slowly, drifting towards sleep. But you are safe. That distance is also comfort, because out here, things happen on scales so vast and timescales so enormous that what might seem dramatic from a distance is, in the experiencing of it, simply slow and immense and quietly magnificent. UY Scuti, like Betelgeuse, is near the end of its life. These swollen red giants are like elderly trees. They have used up most of what they started with, processed it and transformed it, and built increasingly complex elements in their cores over their long lifetimes. And now they are settling into their final phase, their outermost layers draped loosely around them like a great shawl, their cores working on the last stages of nuclear burning that will eventually lead to a dramatic conclusion. But even that conclusion, that eventual explosion, is nothing to fear from this distance. And tonight, in our imagined journey, we are simply visitors, witnesses, gentle observers of something extraordinary. Notice as you drift near UY Scuti how the space around it glows. The star has been shedding gas for a very long time, losing mass into the surrounding space at a rate that is enormous by any measure, but slow by cosmic standards. And that shed material forms a diffuse shell around the star, expanding outward, catching the star's own light and re-radiating it, glowing in soft tones of orange and gold that fade gradually into the darkness of space, like the glow of a lantern seen through fog. The star itself, seen from our vantage point, is a vast, warm, ruddy sphere, deep red at the edges where the gas is cooler and thinner, brighter and more orange toward the center. There are no sharp features, no sunspots, no prominences you could easily identify, just an enormous, gently variable disk of warm, ancient light. Take a breath. Let your eyes, your imagined eyes, rest on this extraordinary thing for a moment. This star has been burning for millions of years. It does not know you are here. It does not know anything, in the way that stars do not know things. They simply are, simply burn, simply exist on scales and time scales that dwarf anything we can easily hold in our minds. And somehow that is comforting. There is something deeply restful about encountering something that is so much larger than yourself, that is so completely indifferent to your existence, that has been here for so long, and will continue in one form or another for so long after you are gone, that your individual concerns and worries and thoughts seem, from this perspective, very, very small. Not unimportant, never unimportant. Your small concerns are real and they matter, but small. And smallness, tonight, is permission to rest. Let the huge, warm, silent star drift slowly behind us as we move on. The night is long, and the universe is generous with its wonders. Part 6. Among the Blue Giants. Not all of the remarkable stars in the universe are enormous in size. Some are extraordinary for a different reason. For their temperature, their ferocious energy, the sheer blazing intensity of the light they produce. We are going to drift now toward a different kind of star. Not a red giant, not a swollen, aging behemoth, but something younger and more fierce. A blue giant. Or, more precisely, a blue hypergiant. Blue stars are hot, extraordinarily hot. While our sun's surface is around 10,000 degrees Fahrenheit, the hottest blue stars have surfaces of 70 or 80,000 degrees or more, sometimes over 100,000 degrees. The difference in temperature produces a profound difference in the color of the light emitted. Cool objects glow red, hotter objects glow orange, hotter still glow yellow, and the hottest of all glow blue-white, a fierce, brilliant, almost painful blue that is the color of maximum temperature. The blue giants are the young ones, the energetic ones, the brilliant burning ones that live fast and, by stellar standards, die young. While a star like our sun might live for 10 billion years, a massive blue star might live for only a few million years before its fuel is exhausted and it ends in a supernova. It burns through 1 million years' worth of fuel in the blink of a cosmic eye. So furious is its energy production. Imagine a great bonfire versus a slow-burning log in a fireplace. The bonfire is magnificent, spectacular, throwing light and heat in all directions, but it is consumed quickly. The log in the fireplace burns low and steady for hours, warming the room without drama. Our sun is the log. A blue giant is the bonfire. We are drifting now past a star called Rigel, a name you might know, because Rigel is also part of the constellation Orion, the same pattern of stars that contains Betelgeuse. Where Betelgeuse is the reddish shoulder of the hunter, Rigel is the blue-white foot, the brightest star in Orion, one of the brightest in the entire sky.
Rigel is about 860 light-years away from Earth. It is a blue supergiant, and its luminosity, the total amount of energy it radiates every second, is about 120,000 times that of our Sun. 120,000 suns worth of energy, pouring out of a single star every single second. But even Rigel is not the most extreme of its kind. There are stars in the universe, rare, extraordinary objects, that make even Rigel seem modest. Stars that are hundreds of thousands, or even millions of times more luminous than our Sun. Stars so bright that if you place them at the same distance from Earth as our Sun, which is to say about 150 million kilometers, their radiation would be so intense that the Earth would be completely vaporized almost instantly, not just scorched, but turned entirely to gas. These stars exist. They are real. They have names and coordinates in astronomical databases, and researchers have spent careers studying their spectra and their behavior and trying to understand their mysteries. And we are going to drift by a few of them, but softly, always softly. There is a region of space in the direction of the constellation Cygnus the Swan, where an extraordinary cluster of stars exists. It is called the Cygnus OB2 Association, a group of massive young stars, many of them blue giants and blue supergiants, that formed together from the same enormous cloud of gas and dust some millions of years ago. They are loosely bound by gravity, spread across a large region of space, and they illuminate the surrounding nebula with their fierce ultraviolet radiation, carving great cavities in the interstellar gas, and sending rivers of stellar wind outward in all directions. We float near the edges of this region. The sky here is extraordinary. In every direction there are bright, fierce, blue-white points of light. Not the soft, warm pinpoints of the night sky from Earth, but hard, brilliant, intense beads of blue fire. Each one a star vastly more luminous than our Sun. Each one blazing with an energy that makes the surrounding space shimmer slightly with radiation. The effect is not unlike floating in a sea of light. A cold, brilliant, fierce light, utterly different from the warm redness of Betelgeuse and Uy-Scuti. This is not the light of a fire dying down. This is the light of a fire at its absolute peak, its fiercest moment, consuming itself with magnificent extravagance. In the heart of this region, partially hidden by dust and gas, there are individual stars whose luminosities are difficult to state without feeling slightly ridiculous. Among the most extreme stars known, sometimes called the luminous blue variables, are objects that radiate energy at rates millions of times that of our Sun. They live on the edge of stability, these stars, radiating so much energy that their outer layers are perpetually on the verge of being blown off by the radiation pressure itself. Imagine a star that is almost too bright to hold itself together, that constantly battles against its own ferocious output. One such class of star is simply called an LBV, a luminous blue variable. These stars, when they are in certain phases of their lives, are among the most luminous stars in the entire galaxy, possibly in the observable universe. They flare and dim, sometimes ejecting enormous shells of gas in violent but slow-motion eruptions, sometimes covering themselves in their own expelled material, so that what we see from the outside is not the star itself, but the glowing cloud around it. The most famous LBV in our galaxy, famous among astronomers at least, is called Eta Carina. It sits about 7,500 light-years from Earth, in the direction of the constellation Carina the Keel, which is visible from the southern hemisphere. Eta Carina is not a single star, but appears to be a binary system, two massive stars orbiting each other, each one extraordinary in its own right,
locked together in a gravitational dance so tight that they complete an orbit in about 5.5 years. The combined luminosity of this system is estimated to be about 5 million times that of our Sun. 5 million. In the 1840s, less than 200 years ago, in the span of human history, Eta Carinae erupted. It brightened enormously, becoming briefly the second brightest star in the night sky, visible even in daylight. Astronomers of that era noted and recorded this spectacular brightening, not knowing exactly what they were witnessing. We understand now that the star expelled an enormous mass of gas, several times the mass of our entire Sun, in a series of enormous, slow eruptions over a period of years, creating a vast, beautiful nebula around it that we can still observe today with our telescopes. 2 great lobes of glowing gas expanding outward from the star like a peanut shape, called the Homunculus Nebula. The homunculus, little man, named for the vaguely anthropomorphic shape of the 2 lobes, though it requires considerable imagination to see it. In the images, it is extraordinarily beautiful. 2 great luminous bubbles of gas, tinged orange and gold, where the dust catches the light, brilliant at the poles, where the star's radiation is most intense, all surrounded by the larger, fainter glow of other material expelled in other eruptions over other centuries. And Eta Carinae is still there, still blazing, still potentially on the verge of a true supernova. The kind that, unlike the eruption of the 1840s, would mark the actual death of the star, rather than just a dramatic phase of its extraordinary life.
Whether it has already exploded, we cannot know. 7,500 light-years is a long time for light to travel. The eruption event of the 1840s we observed was actually the star as it was in the year 6,660 BC, or thereabouts, around the time of the earliest agricultural civilizations in Mesopotamia, around the time of early Neolithic Europe. What the star is doing right now, this moment, we will not know for another 7,000 years or so. Time and space are braided together in ways that make the universe perpetually mysterious, perpetually surprising, perpetually full of secrets we have not yet uncovered. And that is another reason to rest easy. There is always more to wonder about. There is always another mystery. The universe will not run out of things to show us while we are alive to look. Part 7. WR-104, the Pinwheel Star. Deep breath now. We are moving on, drifting through the dark, and ahead of us is something genuinely extraordinary. A star system so visually striking, so geometrically perfect in its strangeness, that when astronomers first imaged it clearly, they spent a long moment simply staring at the data. WR-104 is the name. WR standing for Wolf-Rayet, a class of star named after the 2 French astronomers, Charles Wolf and Georges Rayet, who first identified this type of object in the 1860s. Wolf-Rayet stars are extreme. They are massive, hot, and most distinctively, they are losing their outer layers at an astonishing rate, driven off by the intense radiation pressure from the star's ferocious core. A Wolf-Rayet star sheds mass the way a comet sheds its tail, constantly, continuously, in a stream of material that flows outward into space, called the stellar wind. But the wind from a Wolf-Rayet star is not a gentle thing. It moves at several thousand kilometers per second, fast enough to cross the entire diameter of Earth in a few seconds. It carries material equivalent to the mass of our Sun every 10,000 years or so, which sounds slow until you consider that our own Sun barely loses anything to its solar wind by comparison. WR-104 is about 8,000 light-years away from Earth, in the constellation Sagittarius. It is actually a binary system, a Wolf-Rayet star, paired with a more conventional blue O-type supergiant, both of them massive and bright, orbiting each other with a period of about 220 days. And this orbital dance is what creates something extraordinary. When the 2 stars orbit each other, their stellar winds collide. The wind from the Wolf-Rayet star and the wind from its companion interact where they meet, and the dust and gas that forms in the collision zone
is swept around by the orbital motion of the stars, creating a perfect, beautiful pinwheel. When astronomers imaged WR-104 with telescopes, they saw it. A perfect spiral, coiling outward from the central star system, turning with the orbital period of the two stars. A galaxy in miniature, made of gas and dust and stellar wind, glowing in infrared light. The pinwheel extends outward for enormous distances, each arm of the spiral representing months of continuous outflow. And it is, simply, one of the most beautiful images that modern astronomy has produced. A pinwheel star. There is something meditative about that image. A perfect spiral, endlessly turning, built from the interaction of two extraordinary objects, locked in their gravitational waltz. It is the kind of image that stops your thoughts, the kind of thing you look at and your mind goes quiet, the way it goes quiet in front of a great landscape, or a face you love, or a piece of music that is exactly right. WR-104 has attracted attention not only for its beauty, but because of its orientation. The system appears, from our vantage point on Earth, to be tilted such that one of the poles of the system is pointed fairly directly toward us. Wolf-Rayet stars, when they eventually die, and this system will eventually end in one or possibly two supernova events, can produce a type of explosion called a gamma-ray burst, which releases an enormous amount of energy in the form of gamma radiation in a narrow beam along the star's rotational axis. If the system's axis is indeed pointing toward Earth, and if WR-104 were to explode in a gamma-ray burst, some of that energy might reach us. But here is where we must be careful and precise. 8,000 light-years is far enough that any gamma-ray burst from WR-104 would be diluted enormously by the time it reached us, and our atmosphere provides protection as well. The scientific consensus is that there are other systems where this concern might be more pressing, and that WR-104, while fascinating, is not expected to pose a significant danger to life on Earth. And even if it were closer, even if it were more dangerous, by the time we knew about it, by the time the light from its explosion reached us, 8,000 years would have passed. 8,000 years, in which human civilization might look as different from today as today looks from the Stone Age. The universe keeps its own counsel. We drift near the pinwheel, watching it turn. From here, you can see the arms of the spiral laid out like a nautilus shell, each arm the same as the last, each one slightly smaller as it curls inward toward the bright heart of the system, where the two stars burn. There is something hypnotic about a spiral, something about the self-similarity of it, the way the pattern repeats at different scales, that the mind finds soothing. Breathe with the spiral. Let each breath match the slow, invisible turning of those arms, winding outward into space. Good. Rest here for a moment. The stars around us are quiet. The pinwheel turns. The dark between the arms of the spiral is deep and still. Part 8. The neutron stars, small and strange. Now we turn from the very large to the very small, though small in this context is entirely relative. Not all of the most extreme stars in the universe are enormous. Some of them are extraordinary precisely because of how small they are, how much they have collapsed from something once very large into something almost impossibly dense. When a massive star ends its life, when it has burned through all its fuel, when the nuclear reactions at its core can no longer support the weight of the enormous layers above, the core collapses. In a fraction of a second, what was a core the size of a small planet implodes, compressed by gravity into a sphere perhaps 20 kilometers across. 20 kilometers, the distance from one side of a city to another. That is the size of what is left after the core collapses. And into that 20-kilometer sphere, the material that was once in the core, a mass roughly 1.5 to 2 times the mass of our Sun, is compressed so tightly that atomic structure as we know it ceases to exist. The electrons and protons are pushed together to form neutrons, and the neutrons pack together so tightly that a single teaspoon of neutron star material would weigh about 10 million tons on Earth. 10 million tons in a teaspoon. The density is beyond anything we can produce in a laboratory, beyond anything we have experience with. The only thing denser than a neutron star, as far as we know, is a black hole. And neutron stars do extraordinary things. They spin. When the core collapses, as a consequence of a physical principle called conservation of angular momentum, the same principle that makes a spinning ice skater spin faster when they pull their arms in, the collapsed core spins much faster than the original star did. And some neutron stars spin with extraordinary speed, dozens of times per second, hundreds of times per second, in some cases several hundred times per second.
These rapidly spinning neutron stars are called pulsars because they emit beams of radiation from their magnetic poles, beams that sweep around as the star spins, like the beam of a lighthouse. And if Earth happens to be in the path of that sweeping beam, we receive pulses of radio waves or X-rays with clockwork regularity. The first pulsars discovered, in the late 1960s, produced signals so regular and artificial seeming that the astronomers who found them, briefly and half-jokingly, called them LGM, Little Green Men. Before they understood what they were, the perfectly regular pulses seemed like they might be a signal, an intelligent signal. They were not. They were the most precise clocks in the universe, spinning neutron stars so regular in their rotation that they rival atomic clocks for accuracy. There is something beautiful about a pulsar, this spinning, dense relic of a once enormous star, still broadcasting its position into the universe with every rotation, ticking out its rhythm into the vast silence of space. Like a lighthouse on a rocky coast that everyone has long since stopped sailing past, still faithfully sending out its beam, regardless of whether anyone is watching. The pulsar at the center of the Crab Nebula spins about 30 times per second. The Crab Nebula is the remnant of a supernova that was observed from Earth in the year 1054 AD, a supernova so bright that it was visible in daylight for 3 weeks and was recorded by Chinese and Arab astronomers of the time. Today, almost 1,000 years later, the expanding shell of gas from that explosion is still visible through telescopes as a beautiful, complex, filamentary cloud, lit from within by the pulsar at its heart. Imagine, a star exploded 1,000 years ago. The light from that explosion reached Earth and was seen and noted by people who walked under a different sky, in a world that was, in almost every measurable way, different from ours. And today, the remnant of that explosion is still expanding, still glowing, and at its heart, a neutron star is still spinning 30 times a second, faithfully ticking away, a clock that will run for billions of years with negligible variation. The universe is full of patience. Let that patience settle into your breathing now. Let it slow you, the way the long rhythms of cosmic time naturally slow everything. The heartbeat eases, the muscles loosen, the thoughts come less rapidly and with more space between them. You are drifting through space, and the pulsars are ticking, and the red giants are burning, and the pinwheel stars are turning, and all of it happens at its own pace, unhurried and unworried, and you are part of the same fabric. Part 9. Magnetars, the most magnetic objects known. If pulsars are remarkable, magnetars are something beyond remarkable, something for which we barely have adequate language. A magnetar is a type of neutron star, so it is already the collapsed, super-dense remnant of a massive star, but with something extra. During the collapse of the original stellar core, conditions conspire to produce a magnetic field of extraordinary strength. The magnetic field of a magnetar is somewhere between 100 billion and 10,000 trillion times stronger than Earth's magnetic field. To put that in some perspective, the strongest magnetic fields produced in any laboratory on Earth, powerful enough to levitate frogs, to bend and reshape materials, would be dwarfed by the magnetic field at the surface of a magnetar by many orders of magnitude. If a magnetar were as close to Earth as the moon,
the strength of its magnetic field at our location would be enough to erase every magnetic stripe on every credit card on the planet. It would affect the iron in your blood. And yet magnetars are small, 20 kilometers across, like all neutron stars, completely invisible to the naked eye at any significant distance.
They sit in the dark, spinning, sometimes slowly. They tend to spin more slowly than typical pulsars. They lose their rotational energy relatively quickly to the immense work of maintaining that magnetic field. And occasionally, they do something. Occasionally, the surface of a magnetar, a crystalline crust of neutrons, incredibly rigid and under incredible stress, cracks. The magnetic field shifts, and when it shifts, it releases energy. In December 2004, a magnetar called SGR 1806-20 unleashed what astronomers call a giant flare. In a fraction of a second, it released more energy than our sun releases in 150,000 years. In 0.2 seconds. The burst of radiation swept across space and reached Earth, 50,000 light-years away, and was still strong enough to affect Earth's ionosphere, the uppermost layer of our atmosphere, measurably altering the chemistry of the air at the edge of space. 50,000 light-years away. The burst had traveled for 50,000 years, spreading out in all directions, diluting with distance as the sphere of radiation expanded, and after all that time and all that dilution, it was still powerful enough to leave a measurable mark on our world. What was it like to be near that event when it happened? We cannot know. There are almost certainly no planets near SGR 1806-20, or if there are, they would have been sterilized of any life long ago by the repeated outbursts of this extraordinary object. But if you could be there, at a safe distance, and witness such a thing, it would be nothing like an explosion in the movie sense. There would be no sound. There would simply be a brief, intense brightness, and then it would be over, and the magnetar would be there, sitting quietly in the dark again, spinning slightly more slowly than before, its surface settling back into something close to stillness. Violent things, when they happen in space, happen silently. That is perhaps one of the most important things to understand about the cosmic extremes we are visiting tonight. The energies involved are incomprehensible. But there is no sound in space. No roar, no boom, no crackling. Just light and radiation and the long, patient silence of vacuum. Even the most violent events in the universe happen in silence. And somehow that makes them feel calmer, less frightening, more like weather than like catastrophe. A storm sweeps through, the sky lights up, the magnetar settles, the dark returns, and we drift through it, unhurried, continuing our journey. Part 10. The hypergiant stars at the galactic core. The center of our galaxy is a place of extraordinary density and activity. If you stood on a planet near the galactic center, and planets may well exist there, though the radiation environment would be challenging for life as we know it, the sky at night would be ablaze with stars. Not just dozens or hundreds visible to the naked eye, as from Earth's relatively quiet outer arm location, but thousands, tens of thousands, a sky so crowded with stellar light that true darkness might never fully come. At the very heart of the Milky Way, about 26,000 light-years from Earth, there is a massive black hole called Sagittarius A star, pronounced Sagittarius A star, that anchors our entire galaxy, around which hundreds of billions of stars are slowly and inexorably orbiting in their long galactic years. Sagittarius A star has a mass about 4 million times that of our Sun, compressed into a region smaller than our solar system. It is surrounded by a disk of heated gas and dust, and occasionally it flares and brightens as material falls into it. But most of the time it sits quietly, as quiet as a black hole can be, at the hub of the vast wheel of our galaxy. We are not visiting the black hole tonight. Black holes deserve their own journey, their own quiet and careful attention. Tonight we are pausing here
at the edges of the central region to observe some of the extraordinary stars that inhabit this densely populated part of the galaxy. Among them are several of the most massive and luminous known stellar objects, stars that only form in the crowded, gas-rich environments near galactic centers, where the conditions for creating true stellar giants are most favorable. One of these is a star called the Pistol Star, named for the shape of the nebula around it, which vaguely resembles a pistol in some representations of the data. The Pistol Star is a blue hypergiant, one of the most luminous stars in the Milky Way, with a luminosity somewhere between 1.5 million and 4 million times that of our Sun. The estimates vary because the star is heavily obscured by the dust of the galactic center, and its properties are difficult to measure precisely. Around the Pistol Star is a nebula, the Pistol Nebula, that it apparently ejected in great outbursts about 4,000 to 6,000 years ago. The shell of gas is enormous, spanning several light years, and it glows in the fierce radiation of the star at its center. From Earth, even with the best infrared telescopes, infrared light penetrates the galactic dust more easily than visible light. The Pistol Star and its nebula are difficult to observe. They are hidden in the direction of the galactic center, embedded in layers of interstellar dust that absorb and scatter light, making observation a challenge that requires sophisticated instruments and patient analysis. But in our imagined journey, we can see it clearly. The Pistol Nebula glows around the star like a great luminous cloud, swirling in complex patterns where the star's fierce radiation and wind interact with the material. The star itself is brilliant, a hard blue-white point of light that seems almost too bright, surrounded by the softer, more diffuse glow of the nebula, and beyond that the crowded stellar fields of the galactic center, star behind star behind star in every direction. The whole scene like a night sky multiplied by 1,000. This is not a lonely part of the universe. Here the stars are neighbors, in a way they are not in our quiet corner of the Milky Way. The nearest stars to each other near the galactic center are separated by much smaller distances than the stars in our neighborhood, close enough that a planet orbiting one might on clear nights see its nearest stellar neighbors as objects with visible disks, rather than mere points of light. It is a busier universe, closer to the center. But we are observers from a distance, and we watch the Pistol Star shine, and the nebula glow, and the galactic center shimmer with the combined light of countless suns. And we find in all of this activity a strange peacefulness. The same peace you find when watching a busy street from a quiet cafe window, or a flock of birds wheeling overhead, the individual frantic motion resolving at a distance into a kind of graceful order. The galaxy revolves, the stars burn, the gas and dust drift in great slow rivers, guided by gravity and magnetic fields, and the gentle pressure of starlight. Everything is in motion, everything is changing, and at the same time everything is, at this scale, perfectly still. Change so slow, it is indistinguishable from stillness. Part 11. The Life and Death of Stars. A Meditation. Let us rest here, floating at the edge of the galactic center, and think for a moment about what we have seen. Not to analyze it, not to memorize it, but simply to let it wash over us, the way music washes over you, when you stop trying to understand each note and simply listen. We have seen red giants, swollen and ancient and ruddy, their outer layers draped loosely around them like a garment that no longer fits quite right. We have seen blue hypergiants, fierce and brilliant, and burning at temperatures that vaporize anything that comes near, living fast and hot and brief by stellar standards. We have seen a pinwheel star, coiling its winds into a perfect spiral in the dark. We have seen the remnants of stars, spinning neutron stars, ticking out their pulses like clocks, magnetars, trembling with magnetic forces beyond anything we can replicate. We have glimpsed the crowded center of our galaxy and the extraordinary stars that call it home. And all of these things, every star, every remnant, every cloud of gas and dust, all of them are part of a single, enormous cycle. A cosmic recycling system that has been running since very close to the beginning of the universe, almost 14 billion years ago. Stars are born in clouds of gas and dust. The gas, mostly hydrogen, gathers under its own gravity, slowly, over millions of years, until the pressure and heat at the center become sufficient to ignite nuclear fusion. The star begins to shine. It burns for millions or billions of years, fusing hydrogen into helium, then helium into carbon and oxygen and neon and magnesium, building heavier elements in its core, like a factory building progressively more complex products. When the fuel runs out, depending on the mass of the star, it ends in one of several ways. Small stars, like our Sun, swell into red giants, then gently expel their outer layers in a process that creates a beautiful, expanding cloud called a planetary nebula. A historical misnomer. They have nothing to do with planets, but early astronomers thought they resembled the disks of planets through small telescopes. At the center of the planetary nebula, the bare core of the dead star remains. A white dwarf, a dense, hot, slowly cooling sphere about the size of Earth, but with the mass of a sun, gradually radiating its stored heat into space over billions of years, growing dimmer and cooler, eventually fading to darkness. Large stars, the supergiants and hypergiants, the magnificent extreme objects we have been visiting tonight, end more dramatically. Their cores collapse under gravity in a fraction of a second, triggering a supernova explosion that briefly outshines the entire galaxy, scattering the star's accumulated elements into space and leaving behind either a neutron star or, if the original star was massive enough, a black hole. And the scattered elements, the carbon, the oxygen, the silicon, the iron, all the elements heavier than hydrogen and helium that were forged in the star's nuclear furnace, drift out into the interstellar medium, mix with other gas and dust, and eventually over millions of years are gathered again by gravity into new clouds, new concentrations, new stars. New stars with, sometimes, planets around them. Planets on which, very occasionally, conditions conspire in just the right ways to allow chemistry to happen that is complex enough to call itself life. Life that, over billions of years of evolution, eventually produces creatures complex enough to look up at the night sky and wonder where the stars came from. Creatures like you, lying here in the warm dark, breathing slowly. You are the universe's way of looking at itself. You are what happens when stellar material becomes complex enough to wonder about stellar material. Every atom in your body was forged in a star and scattered by an explosion and gathered again and forged into worlds, and eventually, through the long, patient work of chemistry and biology and evolution and time, became conscious. You are a brief, extraordinary convergence of cosmic processes that has been running since the beginning of time. And you are here, tonight, resting, and that is perfectly sufficient. You have done enough simply by being here, simply by having existed at all. Let your body relax into whatever it is resting on. Feel the support beneath you, the mattress, the pillow, whatever it is. Let your weight settle completely. Let gravity hold you, the same gravity that holds the stars in their courses and pulls gas clouds together into suns and holds you, kindly, to the surface of this small, warm world. Breathe in. Breathe out. The stars are burning. The universe is old, and you are here. Part 12. The Wolf-Rayet stars in more detail. Let us visit a few more of the extraordinary Wolf-Rayet stars, those fierce, mass-losing, rapidly evolving stellar objects that were mentioned briefly when we passed by WR 104. Wolf-Rayet stars are, in many ways, the most visually striking stars to encounter up close. not because they are the largest or the brightest, but because of what surrounds them. The constant, fierce stellar wind blowing off a Wolf-Rayet star creates extraordinary structures in the surrounding interstellar medium. The wind compresses the surrounding gas into bubbles and shells, and the ultraviolet radiation ionizes the gas, causing it to glow in the characteristic colors of excited atoms: hydrogen red, oxygen blue-green, sulfur orange-red. The result is that Wolf-Rayet stars are often found at the heart of spectacular glowing nebulae, surrounded by the material they have expelled over their lifetimes, shaped into complex structures by the wind and radiation of the star itself. One of the most beautiful examples of a Wolf-Rayet nebula is NGC 2359, also called Thor's Helmet Nebula, because in images it resembles a great winged helmet, broad at the crown and trailing two arching plumes behind it, like the helmet of a Norse god, rendered in glowing gas.
At the center of Thor's helmet is a Wolf-Rayet star called WR7, blazing away, driving the gas around it outward with its fierce wind, creating the great bubble at the center of the nebula and the elaborate wings of compressed material that give the object its distinctive shape. From a distance, Thor's helmet is a spectacular sight, a jewel of the night sky, glowing in soft blues and greens at the edges, where the gas is thin and the ionization is partial, brightening to white and yellow closer to the central star, where the radiation is most intense. The wings sweep outward and curve slightly, giving the whole structure a sense of motion, as if the nebula were sweeping through space like a vast cosmic bird, or like a god's helmet falling slowly through the dark. In reality, the nebula is mostly stationary. The expansion is slow enough that it would take centuries to detect any motion, but the impression of motion is there, embedded in the shape. There are other Wolf-Rayet nebulae, each one extraordinary in its own way. There is the Ring Nebula in Lyra, a famous, beautiful object, a circular ring of glowing gas around a dying star, seen nearly face-on from Earth, so that it appears as a perfect smoke ring in the sky, tinged blue at the edges and yellow toward the center. There is the Helix Nebula, sometimes called the Eye of God Nebula, because its overall structure, seen from Earth, resembles an enormous eye peering out from the depths of space. A great circular structure of gas with a bright center, surrounded by filaments and tendrils of material, extending far into the surrounding space. These nebulae are the exhaled breath of dying stars, the last exhalation of a long, stellar life, puffed outward into the surrounding medium, lit from within by the still hot core at the center, glowing for tens of thousands of years before the core fades and the gas disperses and the nebula dissolves into the interstellar medium, becoming part of the thin, diffuse material from which future stars will eventually form. Everything comes back. Nothing is lost, in the cosmic sense. The material that makes up a nebula will, in 1 billion years or less, be part of new stars, new planets, perhaps new living things. The atoms do not care what form they take. They are simply atoms, responding to the forces that act on them, forming complex structures when conditions permit, dispersing when conditions change, forming again in new configurations. The patience of matter. We drift past Thor's helmet, watching the wings of gas sweep silently past us, the central star blazing blue-white at the heart of the bubble, the filaments of the nebula reaching out in all directions, like the arms of a luminous creature reaching for the dark. It is very beautiful. Let that beauty settle into you like warmth. Part 13. The Variable Stars and Their Long Rhythms. There is another class of remarkable stars we have not yet properly visited, the long-period variable stars, or Mira variables, named after the prototype of the class, the star Mira, in the constellation Cetus, the whale. Mira is a red giant star, significantly less extreme than the stars we have been visiting, much less luminous, much less massive, much closer to the evolutionary path that our own sun will eventually follow. But what makes Mira and its class remarkable is the long, patient, beautiful rhythm of their variability.
Mira dims and brightens over a period of about 332 days, approximately 11 months. At its brightest, it can be one of the more prominent stars in the sky, easily visible to the naked eye. At its faintest, it disappears entirely from unaided vision, becoming a telescopic object. And then, slowly, over months, it brightens again and returns to visibility, and the cycle continues. It has been doing this for a very long time, and the variation is caused by pulsations of the star itself, the outer layers expanding and contracting in a long breathing rhythm, changing the star's radius and temperature, and thus its brightness over the course of nearly a year. When you look at Mira with this in mind, it becomes something almost meditative. A great ancient star, breathing slowly in the dark, its breath taking almost a year per cycle, steady and predictable, in a universe that is, in so many other ways, wildly unpredictable. The Mira variables are the slowly breathing giants of the stellar world, their rhythm so long that a human lifetime would encompass only a few dozen cycles. There are thousands of Mira variables known in our galaxy, red giants near the ends of their lives, all pulsing away, each with its own period, its own particular rhythm, its own brightness range. Together they form a kind of slow cosmic heartbeat, a vast, distributed pulse of the Milky Way, so spread out and so slow that no one will ever hear it, except by spending careful years at a telescope, recording and comparing, and building up the long curve of light over time. Astronomers who study variable stars often develop what seems to outsiders like a peculiar affection for their subjects. They speak of their stars, check on them regularly as if checking on old friends, note with interest any deviation from the expected pattern, and wonder what it means. The stars, of course, know nothing of this attention.
But the attention is real, and it is a form of care, the care of curious, patient minds for objects that are very old and very far away, and very much beyond our ability to change or affect in any way, but that we watch regardless, with love, because they are beautiful, and because they are there. We float near a Mira variable now, an unnamed one, a representative of the class, glowing deep red in the dark, its outer layers slowly expanding outward in one phase of its long breath. The expansion is invisible on human timescales. We would need to watch for months to see the change. But knowing it is happening gives the view a quality of quiet dynamism, of hidden motion, like watching a sleeping person whose chest rises and falls so slowly that you need to look for several breaths to be sure the movement is real. The star breathes. The dark holds it. We drift on. Part 14. A galaxy full of stars. We have been visiting individual stars tonight, up close, immersed in their light and their gas and their extraordinary properties. But let us pull back for a moment, very far back, so far that individual stars become invisible, and instead we see the whole galaxy they inhabit. We are pulling back now, drifting away from the galactic plane, rising above the disk of the Milky Way, as if we are gradually ascending in a great silent elevator, and the galaxy spreads out below us, and then around us, and then everywhere. And it is extraordinary. The Milky Way is a barred spiral galaxy, a disk of stars and gas and dust, about 100,000 light-years in diameter, with a central bar of stars, and 4 main spiral arms trailing outward from the ends of the bar. Each arm a great concentration of gas and star-forming regions, winding out in graceful curves, and then gradually dispersing into the general field. From above, from our elevated vantage point, above the galactic plane, it looks like a pinwheel, like a WW-104, but made of hundreds of billions of stars instead of 2 stellar wind streams. The resemblance is not coincidental. Spirals appear at many scales in nature, and the mathematical reasons for their appearance are the same at the scale of a solar wind nebula and the scale of a galaxy. Different numbers producing similar forms
through similar physics. In the center of the galaxy, the bar of stars glows brighter than the rest, a yellowish-white glow dominated by older, cooler stars that have been gathering in the central region for billions of years. On either side of the bar, the spiral arms begin, winding outward, marked by the blue-white brilliance of young, hot stars and the pink-red glow of hydrogen nebulae, where new stars are still forming. Our sun is in one of those arms, the Orion Cygnus arm, a relatively minor arm or spur between two larger arms, located about 26,000 light-years from the center. We are neither near the center nor near the edge. We are, in the cosmic fashion, fairly average in our location, in a quiet neighborhood of a large galaxy, orbiting the center at a speed of about 800,000 kilometers per hour, completing one galactic year, one full orbit around the galactic center, in about 225 million years. The last time our solar system was in the same position in the galaxy as it is now, dinosaurs had not yet existed on Earth. The time before that, not even multicellular life had yet evolved. That is how long a galactic year is. The galaxy rotates, slowly. All those hundreds of billions of stars, each orbiting the center in its own path, at its own speed, the whole thing maintaining its spiral structure through a combination of orbital mechanics and gravitational dynamics that is still being actively studied and better understood. From above, the glow of the galaxy is beautiful and calm. There are no sharp edges. The density of stars and gas fades gradually from the bright central bar outward through the arms and into the sparse outer disk, and beyond the disk, an even sparser halo of old stars and globular clusters stretches out for hundreds of thousands of light-years in all directions. And around the Milky Way, at enormous distances, are other galaxies. The large and small Magellanic Clouds, companion dwarf galaxies, visible from Earth's southern hemisphere as small, separate patches of light against the dark, hover nearby, gravitationally bound to the Milky Way, slowly being absorbed. The Andromeda Galaxy, 2.5 million light-years away, a spiral similar in size to our own, is approaching us at about 110 kilometers per second, and will eventually, in about 4.5 billion years, merge with the Milky Way in a slow, magnificent galactic collision that will last for billions of years itself. 4.5 billion years. There is no need to hurry. There is no need to worry. The galaxies drift toward each other at speeds that are, by cosmic standards, leisurely. The merger, when it comes, will not be a violent crash, but a slow dance. Stars and gas and dark matter interpenetrating over millions of years. The two galaxies passing through each other and swinging around and passing again, gradually settling into a single larger galaxy over a period of time that makes any human concern seem microscopic by comparison. We float here above the Milky Way and watch it turn very slowly, the way a child might lie in a field and watch clouds move. Not rushing, not analyzing, just watching the slow, graceful motion of enormous things. The galaxy turns. The night is long. And you are growing sleepier, I think. Good. Part 15. The Birth of Stars, Pillar and Cloud. Let us drift back down now, back into the plane of the galaxy, and visit a place where stars are being born. There are regions of the galaxy, and similar regions in all galaxies, where the gas and dust of the interstellar medium is in the process of collapsing under its own gravity, gathering into dense cores that will eventually, over millions of years, ignite as new stars. These regions are called stellar nurseries, or star-forming regions, and they are among the most visually spectacular places in the universe. The most famous image of such a region, one of the most famous astronomical images ever taken, is known as the Pillars of Creation. The Pillars of Creation are part of the Eagle Nebula, a star-forming region about 6,500 light-years from Earth, in the constellation Serpens. When the Hubble Space Telescope photographed this region in 1995, the result was an image so beautiful, so striking, so immediately and powerfully evocative, that it became one of the iconic images of our time. reproduced on posters and books and websites and clothing, used as a metaphor for creativity and new beginning, recognized by millions of people who would not have been able to name any other astronomical image. The pillars themselves are enormous columns of gas and dust, several light years tall, rising from a larger cloud of material. They are the remnants of a denser part of the original gas cloud, partially eroded by the radiation and stellar winds of the hot young stars that have already formed in the surrounding region. The pillars are being slowly eaten away, photo-evaporated, astronomers call it, the gas at their surfaces being heated by ultraviolet radiation until it escapes into space. But inside the pillars, protected by the dense gas above them, small, dense cores of material are condensing, slowly, incredibly slowly, over hundreds of thousands of years, into protostars that will eventually ignite and shine.
The tips of the pillars are particularly striking. They glow in the fierce ultraviolet radiation of nearby stars, lit up like the tips of candles, and from the tips, streamers of gas flow outward into the surrounding nebula, like smoke from a slow fire. We float near the pillars of creation, and the effect is overwhelming. These are objects so large that a single pillar, seen from the side, would span the entire diameter of our solar system many times over. They are immense, dark and dense at their hearts, glowing at their edges where the radiation reaches them, and beautiful, unutterably beautiful, in the way that only things of great antiquity and great scale can be. And at the heart of one pillar, too deep inside for the light to easily escape, but present, we know, from other wavelengths of observation, a small knot of material is slowly condensing. It has been condensing for thousands of years. It will continue for thousands more. But eventually, inevitably, as the density and pressure and temperature at the center of that knot climb higher and higher, something will happen. A threshold will be crossed, and a new star will begin to shine. It will not be dramatic. There will be no flash, no announcement. The ignition of nuclear fusion in the core of a new star is a gradual process, a slow awakening, the star growing hotter and more luminous over thousands of years, until it is finally, undeniably, a star. And then it will shine for millions or billions of years, burning its hydrogen, fusing its helium, building complexity in its core, until its fuel runs out, and it too, like all the stars before it, dies and gives its material back to the universe. The cycle. Always the cycle. Stars are born, and stars die, and the material they were made of is never lost, only transformed, endlessly cycling through different forms. Gas, star, nebula, white dwarf, neutron star, black hole, and back again to gas, in a great, patient cosmic recycling that has been running for 14 billion years, and will continue for billions or trillions more. There is comfort in cycles. The seasons cycle, the tides cycle, the stars cycle, though on timescales we can barely grasp. Everything returns. Everything continues. And tonight, drifting near the pillars of creation, watching the slow birth of new stars deep in their dark hearts, you are witnessing the universe doing what it has always done, making more of itself, building complexity from simplicity, light from dark, structure from chaos, with infinite patience and extraordinary grace. Breathe slowly. You are part of this. You are one of the universe's structures, one of the forms it has taken, a temporary but extraordinary arrangement of atoms that can look at other arrangements of atoms and wonder about them, and find them beautiful. That is remarkable. Rest with that for a moment. Part 16. The Mystery of Dark Stars and the Edge of Seeing. There are stars we cannot see, not because they are too faint or too far away, but because they have crossed a boundary from which no light can return. They have become black holes, the ultimate end state of the most massive stars, objects so dense that their gravity prevents even light from escaping. We will not linger long here,
because black holes are a subject that deserves their own careful, separate journey. But in a survey of the universe's most extraordinary stellar objects, they cannot be left unmentioned. When the most massive stars, those with original masses perhaps 20 or more times our Sun, complete their lives and their cores collapse, the collapse does not stop at the neutron star stage. The gravity is too strong.
The core keeps collapsing, past neutron star density, past any density that any known force can halt, down to a point of infinite density, a singularity, surrounded by a boundary called the event horizon, from inside which nothing, not even light, can escape. The black hole is born. It is, in a sense, the most extreme form of stellar evolution. The star has not died, but transformed so completely that it has become something entirely different, something that no longer radiates its own light, but rather bends and distorts the space around it, capturing everything that comes too close, and revealing its presence only by its effects on the matter and light around it. Near a black hole, at a safe distance, observing without approaching too closely, the view is extraordinary. The black hole itself is invisible, a dark sphere, the event horizon, surrounded by the distorted light of everything behind it. The gravity of the black hole bends light from stars and gas clouds behind it, creating a halo of distorted light around the dark center, a photon ring, a bright ring of light that circles the black hole's shadow, the result of light rays that have been bent into near-circular paths by the extreme gravity. If the black hole is actively accreting, drawing in material from a surrounding disk of gas, the disk itself glows fiercely, heated by friction and compression to temperatures that produce X-rays and gamma rays and intense visible light. A brilliant, hot, rapidly rotating disk spiraling inward toward the event horizon, with relativistic jets of material sometimes shooting outward from the poles at nearly the speed of light. These are active black holes, quasars, and active galactic nuclei. The most luminous objects in the universe are powered by supermassive black holes, millions or billions of times the mass of our Sun, actively consuming material from enormous accretion disks, outshining their entire host galaxies, with the energy released by matter falling into the ultimate darkness. But tonight, we will observe from a respectful distance, and then move on. The black hole is there, anchoring its part of the galaxy, bending space, accumulating mass, waiting with its particular infinite patience for whatever comes within range of its gravity. We are not in range. We are safe and drifting, and the black hole grows smaller behind us as we move on, and the ordinary darkness of space returns, and the stars ahead of us shine steadily and warmly in the dark. Part 17. The Long Lives of Old Stars. We have spent most of our journey among the young and the dramatic, the enormous, the fiercely bright, the violently evolving. But let us visit briefly a place of great age and quiet. Globular clusters are among the oldest structures in our galaxy, roughly spherical collections of stars, sometimes containing hundreds of thousands of stars, tightly bound together by gravity, orbiting the galactic center at great distances, often hundreds of thousands of light years above or below the galactic plane. The stars in globular clusters are extraordinarily old. Most were formed in the very early universe, 12 or 13 billion years ago, only a billion years or so after the Big Bang itself. They have been together ever since, gravitationally bound in their compact spheres, slowly circling the galaxy on their long orbital paths, while the galaxy itself formed and evolved around them. The stars in these clusters are old. The most massive ones have long since burned out, completed their stellar lives, and died, leaving behind white dwarfs and neutron stars in the cluster. What remain as still shining stars are the lower mass ones, stars smaller and cooler than our Sun, burning slowly on their vast reserves of hydrogen, still shining after more than 12 billion years, still adding their quiet light to the collective glow of the cluster. When you look at a globular cluster, any of the hundreds known in our galaxy, you are looking at some of the oldest light in the universe.
The photons leaving those stars were produced by nuclear reactions in the cores of stars that were already ancient when our solar system formed. When our sun was being born, those stars were already older than our sun is now. The effect of floating near a globular cluster is extraordinary. In every direction, wherever you look, there are stars. Close together, much closer than stars are in our neighborhood, so that the sky has no truly dark patches between the stars, but is instead a mosaic of stellar light. Every direction you turn providing more stars, fainter and more numerous toward the outskirts of the cluster, brighter and more densely packed toward the core. The combined light of the cluster is warm and golden. These old stars are smaller and cooler than the sun, tinged orange and yellow, their ancient light the color of late afternoon, of autumn, of things that have lasted a long time. It is a peaceful place. Among all the extraordinary, extreme, dramatic stellar objects we have visited tonight, the globular cluster is perhaps the most restful, a community of old, patient stars that have been shining quietly for most of the universe's history, that have outlasted the supergiants and hypergiants and Wolf-Rayet stars that were their contemporaries in the early universe, simply by virtue of burning slowly, patiently, without extravagance. There is wisdom in that. Long, slow burning, steady output, patient continuation. Like a breath, taken and released and taken again. Like a heartbeat, regular and quiet.
Like sleep, coming gently, not forced, not rushed. The old stars of the globular cluster have been shining for 12 billion years. You have been awake today. You have done things, thought things, experienced things. And now the day is done, and you are resting, and the time for rest is here. Let the old stars shine behind you as you drift deeper into the quiet. Part 18. The Great Quiet. We are deep in space now, deeper than we have been. Around us the stars are fewer. We have drifted beyond the crowded regions of the galaxy, out into the intergalactic medium, the vast, nearly empty space between galaxies. Out here, the density of atoms is even lower than within a galaxy. A few atoms per cubic meter, perhaps, the lowest densities in the universe. Out here, the darkness is the most complete darkness that exists. And yet, even here, it is not truly dark. Every direction you look, in every direction, distributed across the whole sky, there are galaxies. Faint, small, distant, but there. In the famous deep field images taken by the Hubble Space Telescope, photographs made by pointing the telescope at a tiny, apparently empty patch of sky and collecting light for days, the resulting image shows not emptiness, but thousands of galaxies. Different shapes, different sizes, different colors, spirals tilted at different angles, ellipticals glowing golden yellow with their old stellar populations, irregulars and merging pairs, and everything in between. In that tiny patch of sky, smaller than a grain of sand held at arm's length, there are thousands of entire galaxies, each one containing hundreds of billions of stars, each one with its own extraordinary stellar objects, its own red giants and blue hypergiants, and neutron stars and black holes, its own nebulae and star-forming regions and globular clusters, its own slowly rotating disk of cosmic matter and meaning. The universe contains an estimated 2 trillion galaxies. 2 trillion. And each of those galaxies contains, on average, hundreds of billions of stars. And around some fraction of those stars, we do not know exactly what fraction, but the early results of the Kepler Space Telescope and other planet-hunting missions suggest it might be the majority. There are planets. The universe is full of worlds. Whether it is full of life, we do not yet know. That is perhaps the greatest open question in all of science. Are we alone? Or are we one instance of something that happens everywhere, when conditions are right? The answer, when we eventually find it, will be one of the most profound pieces of information in human history.
But we don't need to find that answer tonight. Tonight, we can simply wonder. We can float here, in the great quiet between galaxies, and let the immensity of it wash over us, without needing to do anything with it, without needing to draw any conclusions, or reach any destinations, or accomplish any goals. We are here. The universe is here. The 2 trillion galaxies are here, each one glowing faintly with the combined light of hundreds of billions of suns, each one a world unto itself, each one carrying within it extraordinary things. And we are one small instance of the universe looking at itself and being amazed. That is enough. That is everything. Breathe. Part 19. Coming Home. We have traveled far tonight. We have visited Betelgeuse, the great red giant, breathing slowly 700 light-years from home. We have drifted near UY Scuti, the largest known star, so immense that a commercial flight around its equator would take 1,000 years. We have seen the fierce blue brilliance of Eta Carina, expelling its shells of gas in great, slow eruptions. We have watched the pinwheel of WR-104 coil its stellar winds into a perfect spiral. We have passed by neutron stars, spinning their lighthouse pulses into the dark, and magnetars trembling with magnetic forces beyond anything on Earth. We have seen the pillars of creation, those extraordinary columns of gas and dust where new stars are slowly awakening. We have glimpsed the globular clusters and their ancient, patient stars, and we have floated in the deep intergalactic quiet and let the immensity of 2 trillion galaxies settle gently around us. And now we are turning. We are turning back, and the Milky Way is ahead of us again, approaching slowly, not as a band of haze this time, but from outside, as a galaxy, a beautiful barred spiral seen from above, its arms curling outward from the central bar, dotted with the brilliant points of star-forming regions. We are diving back in now, gently, like a leaf settling onto the surface of a still pond. The galaxy grows around us. The stars become individually distinguishable as we enter the disk, and we slow and drift and find our way back through the familiar outer arm to our quiet neighborhood. The sun is ahead, our sun, yellow-white, steady, ordinary and extraordinary. The same sun that makes the light that falls on your face every morning, that drives the seasons and the weather, and the growth of every plant you have ever seen. And there, circling it in its blue-white sphere of water and cloud, is Earth, your world, the world where you are lying right now, warm and safe, your breathing slow, your body heavy with the comfortable weight of rest. We are coming home. The planet grows ahead of us, and the details of it emerge. Continents and oceans, the curve of the horizon, the thin shell of atmosphere that glows faintly blue at the edge of the world where it catches the sunlight. There are clouds swirling over the ocean in great spiral storms, and mountain ranges casting long shadows, and at the edges of the night side, tiny clusters of light where cities have gathered. And there is your city, your neighborhood, your home, and there you are, lying down, comfortable, breathing slowly. We have returned. Part 20. The stars above the sleeping world. Outside right now, the stars are there. Even if you cannot see them, even if clouds cover the sky, even if the lights of your city wash out all but the brightest, they are there. Betelgeuse is there, its red light traveling toward you, 700 years on its way. UY Scuti is there, 9,500 light-years away, breathing its slow, variable breath. WR-104 is there, turning its pinwheel in the dark. The globular clusters are there, their ancient stars shining patiently. The pillars of creation are there, harboring their slowly forming stars in the dense hearts of their gas columns. And the universe is there, all of it, vast and old and quiet and full, surrounding your small, warm world on all sides, above and below, and in every direction, in the great dark between the stars, and in the slow turning of the galaxies, and in the patient ticking of the pulsars. It is all there. It has always been there. It will be there tomorrow morning when light comes, and it will be there tomorrow night when you look up again. The sky is not empty. It never was. Every point of darkness between the stars is filled with something. Distant galaxies, intergalactic gas, the faint background glow of the Big Bang itself, still traveling in all directions after nearly 14 billion years. And every point of light is a sun, with its own system, its own history, its own contribution to the great ongoing cosmic story. You are part of that story. Your atoms are old, most of them made in stars that died before the sun was born. And some of the hydrogen atoms in you are among the oldest things that exist, forged in the Big Bang itself, 13.8 billion years ago. You are made of the oldest material in the universe, temporarily arranged into a conscious, breathing, wondering creature, lying in the dark of a Tuesday or a Wednesday, or whatever night this happens to be, on a small rock circling an ordinary star, in a quiet arm of an ordinary galaxy. And that is wonderful. Not ordinary wonderful, in the way we casually call things wonderful without really meaning it. Truly, deeply, genuinely wonderful, full of wonder, worthy of wonder, something that rewards thinking about, and that reveals more the more you think about it. But tonight, you do not need to think about it. Tonight, you simply need to rest. The stars will not stop being there because you stopped thinking about them. The universe will not stop being vast because you closed your eyes. Everything will continue without your attention for a few hours, and when you open your eyes again, it will all be here, waiting with the same patience it has always shown. The same patience it showed when you were a child, and before that, when your grandparents were children, and before that, when there were no people on earth to look up and wonder. The universe is patient, and you have been patient tonight in your own way, patient enough to travel with me through the dark, to visit the giant stars and the ancient clusters, to float above the galaxy and drift through the intergalactic quiet. Now it is time for the final part of the journey. Part 21. The Great Quiet Stars of Old Age, White Dwarfs. Before we arrive fully at rest, there is one last place I want to take you. Not one of the giants, not one of the fierce, bright, violent-seeming objects we have been visiting. Something much smaller, much quieter, much closer to what your own sun will eventually become. White dwarfs. These are the remnants of small to medium stars, stars like our sun, that have completed their long lives, shed their outer layers in the gentle puff of a planetary nebula, and left behind their naked cores. White dwarfs are small, roughly the size of Earth, though containing roughly the mass of the sun. They are incredibly dense. A teaspoon of white dwarf material weighs about 5 tons on Earth. And they are hot. Initially, very hot, with surface temperature